Hi guys, my name is Danica Dvorak and I am going to be doing a tutorial of problem 6.1.2 from Operations Research and Introduction. This is for my Engineering 340 class at Liberty University and I hope that it is helpful for you. The prompt for this problem says that we need to construct the dual problem for each of the following linear programming models fitting the standard form. So today I'm going to teach you guys how to set up a dual problem. It's a pretty simple process, but there are a few little rules to be aware of. So there's two parts for this prompt. Part A says that we need to find the dual problem for the linear programming model back in problem 3.1.5, and that problem is listed below. We need to maximize the objective function z equals 10x1 plus 20x2, subject to the three constraints negative x1 plus 2x2 less than or equal to 15, x1 plus x2 is less than or equal to 12, and 5x1 plus 3x2 needs to be less than or equal to 45, and both x1 and x2 need to be greater than 0. The second part of the prompt, part B, says that we need to find the linear programming model in problem 4.7.6, and that linear programming model is listed below as we need to maximize the objective function z equals 2x1 minus 2x2 plus 3x3, subject to the three constraints negative x1 plus x2 plus x3 is less than or equal to 4, 2x1 minus x2 plus x3 is less than or equal to 2, and x1 plus x2 plus 3x3 is less than or equal to 12, and as usual, all three of those variables, x1, x2, and x3 need to be less than, or they need to be greater than, greater than or equal to 0. So we are going to just start right in with solution for part A. The prompt is given here again, but I reorganized it so that all the x1 variables are lined up and all the x2 variables are lined up. We're going to start with this first problem, part A, because this one only has 2 variables, whereas part B has 3 variables, so it's a little more tricky, but the general concept is the same. So in order to make a dual problem, what we are doing is flipping the x and y axes, basically. So we want to make an objective function that has y variables instead of x variables. And there will be as many y variables as there are constraints in this original problem. So since there are 3 constraints here, there will be 3 y variables. Another thing to know is that when we say we want to maximize the objective function in the original problem, that means we are going to want to minimize in the dual problem. We are going to want to minimize. Oh, my cursor is not wanting to work. We are going to want to minimize that objective function for our dual problem. Our objective function that we want to minimize in the dual problem is going to be based off of the coefficients of the constraints here. So we are going to say that this first constraint is like our y1. We're going to say that the second constraint is for our y2 variable, and that our third constraint is like our y3. There's some correlation there. So our minimizing function, each of these coefficients on the end here is going to become the coefficient for that new y variable. So our minimizing, we want to minimize the objective function 15y1 plus 12y2 plus 45y3. That's going to be our objective function in the dual problem. We also do need constraints though. So in this problem, we are only going to have two constraints. Let's do this first constraint in red here. The very first constraint is going to follow here. And our second constraint, we'll do this one in green, is going to follow here. So you're almost kind of like how in the dual problem we want to flip the axes. We're almost kind of flipping the problem here in order to find the dual problem. So the way we're going to read this, is that we're going to have negative y1 plus y2 plus 5y3 needs to be greater than or equal to 10. Because we had less than or equal constraints in our original problem, we're going to flip those to be greater than or equal to in our dual problem. Just like how we, instead of maximizing our objective function, we're going to minimize it now. This is another thing where we kind of flip it. So that's our first constraint. Our second constraint is going to be 2y1 plus y2 plus 3y3 is going to be greater than or equal to 20. This and statement at the very bottom here, that x1 and x2 need to be greater than 0, that one kind of stays the same for our dual problem. We're going to say that y1, y2, and y3 all do need to be greater than or equal to 0. This one you don't flip. It doesn't need to be less than or equal to 0. It stays greater than or equal to 0. So we can see here, this was the solution I had previously typed up, but we can actually see it written out here. The objective function for this dual problem is going to be that we minimize the objective function 15y1 plus 12y2 plus 45y3. And just to show that it's a dual problem, instead of saying z, we say v. It just kind of is a notice to the reader that, hey, we're doing a dual problem. And we need it to be subject to the two constraints we pulled out. Negative y1 plus y2 plus 5y3 is greater than or equal to 10. And 2y1 plus y2 plus 3y3 is greater than or equal to 20. And we kept the greater than or equal to 0. I am missing a y3 here. Just kind of forgot to add that in. So we'll just kind of add that in. All three of those variables should be greater than or equal to 0. So now that we understand the general gist of how to do a dual function, we're going to do the second problem. This one's a little trickier because there's a little bit more to this problem since there's a third variable, but I'm pretty confident we can do it. So once again, the same rules apply, where in this case we are maximizing the objective function, which means that we are going to want to minimize the objective function in our dual problem. That concept stays the same, so we are going to minimize. The next thing we want to notice is that there are three constraints once again. So we can restate these as kind of being equivalent to our y1, our y2, and our y3. There's three constraints. There's going to be three y variables. And we can circle these end coefficients to say that those are going to be the new coefficients for our objective function. So our new objective function for the dual problem is going to be 4y1 plus 2y2 plus 12y3, and we are going to minimize that objective function. Okay, so for our first constraint, we'll do it in red. We just kind of circle all the x1s that we have previously lined up. Going to do our second constraint with green from the x2s, and we'll do purple for our last constraint of the x3s. So we can kind of just read right up here again. We're going to have, let me switch back to red. We're going to have negative y1 plus 2y2 plus 1 y3 is going to be greater than or equal to 2. And we're doing greater than because it's different from this less than or equal to. So we're going to do greater than or equal to 2. Our second constraint, we can read right off, it's going to be 1y1 minus y2 plus y3 is going to be greater than or equal to negative 2. You have to remember this negative sign here. Okay, and then our final third constraint is going to be y1 plus y2 plus 3y3 is going to be greater than or equal to 3. And the final thing we need to remember is this and down here. That is going to stay the same in the regard of this greater than or equal to. So we're going to say and y1, y2, and y3 are all going to be greater than or equal to 0. So let's check out if we did that correctly. So here is that previously recorded solution. We did say that we wanted to minimize this objective function, so we got that right. And we said 4y1 plus 2y2 plus 12y3, and those coefficients were coming from the less than or equal to coefficients from the previous constraints. We got that right. And once again, instead of saying z for the objective function, we just say v in order to notify the reader that, hey, this is a dual problem. And then we said that there were going to be 3 constraints with 3 variables, so we got that right. And it looks like these all check out. Remember, these numbers over here were coming from the coefficient of the first problem, the z objective function. And each of these coefficients were us just reading up the previous constraints. And we have y1, y2, y3 are all greater than or equal to 0. So it looks like we did this correct as well. If you have any other questions about dual problems, how to set those up, or how to solve them, please comment in the comments below. A side note about dual problems, one of the reasons why we would do this or why this is so helpful is sometimes when we flip the x and the y axes like that, we can solve graphically, where before in the original problem we couldn't. It kind of gives us another angle to come at it by. Sometimes that doing it by a dual problem is easier. Sometimes it's faster to find the answer that way. Another reason is that both of these answers, or both of these ways of solving for these objective functions, you end up getting the exact same solution. So if you're not sure that you did the original problem correct, you can always change it into a dual problem and double check your answer, because both solutions are going to be the exact same number. I hope this was really helpful. If you have any questions, once again, comment below and I will try and answer them. Thanks!